I'm Mark Yatskar. I guess there's people listening somewhere, maybe. And there's a few people here. First, just thanks, Minjun, for inviting me to come give a talk here. I'm going to be talking, I guess, mostly to you guys, but about some work I do in language and vision. Currently I'm a postdoc in Seattle at a place called Allen Institute of AI. And I'm just going to jump right in. And so basically, I'm motivated to thinking about kind of language and vision applications. And my motivating thesis is really like, how do we build an intelligent system that can recognize the visual world? And one kind of important question before you set forth on something like this is, why would you bother doing this? And really, there's kind of current day applications. So this is important for Google image search. You know, when you guys, or whatever kind of image search you're doing, these kind of ideas are required to make that work. Kind of near term in the future, there's kind of an assistive technology kind of perspective on this. If you have someone who can't see, how do you kind of help them navigate the world in ways that they can understand? But then kind of really far out, like, well, when we put robots in the world, right? These robots will have to simultaneously see and understand, but also be able to communicate about what they're seeing, and in a way that we understand as well, right? So that's kind of that joint problem. So then if you have those applications in mind, you would say, okay, how do we build an intelligence that can recognize the visual world? Okay, query, robot, what is our purpose? One way to kind of go about this might be, okay, tell the robot to explore the world until it just finds concepts. And so how might this look? There might be a robot kind of wandering around, looking, picking things up, and eventually find something like a flower. And say this one robot names it flower. And tells everybody else. And everybody kind of needs to continue interacting with this flower until something happens, right? So one of these robots will just stare at it, nothing happens. One robot might just run it over, nothing happens. A few more stare at it, nothing happens. And until maybe like a few try to like put a flower out, nothing happens. And everyone's kind of disappointed. And maybe eventually one of these robots discovers that flower is actually kind of a thing you can give to another agent. And so now flowers are givable, and we've kind of made progress and discovered something new about flowers. But there's kind of a problem with this, and the biggest ones are what actually compelled these agents to discover flower. So that's unclear in this setup. How long will we have to wait for this to actually emerge from our kind of visual intelligence? And will they actually learn everything that we currently understand about the world and want to communicate about through this process of discovery? And so my work is actually different than this. It kind of sidesteps this by treating language and vision together. And so my kind of hypothesis is, well, we're going to need to explicitly supervise with language structured visual data. So it's going to be a joining of language and vision. And what do I really mean by this? Okay, so the data should be multimodal, so it should involve images. It should be language-based, so it's going to also involve words. And it's kind of the new bit that I'm going to talk about is it's going to involve implicit language structure. So we're going to analyze visual data from the point of view of word-word relationships. To kind of put this in context for kind of the broader computer vision world, there's kind of like two kind of ways about thinking about this. So the kind of first way is weakly supervised. This is kind of like world discovery. Agents don't know anything explicit about the semantics of what's going on, nothing about language. And there we're trying to learn the structure of the world through proxy tasks. So this is called weakly supervised kind of learning. And there will be something like, for example, colorization. You take an image, you subtract its color, and then you try to make a representation from moving from an uncolored image to a colored image. And then there's a whole other side of this, which is called supervised learning. And basically, these are all kind of well-known problems in computer vision. So ImageNet is kind of the basic classification problem in computer vision, but there's all of these other ones. And so there's this divide between which of these is actually the way to make a visual system. And currently, actually, the right-hand side is largely winning. The left-hand side, we don't know how to build effective models in that regime that actually understand the semantics of the structure of the world. And it turns out everything I've listed in this column on the right actually implicitly or explicitly is already language-based. So the ones on the bottom, question, answer, and captioning, those are kind of maybe obviously language-based. But something like ImageNet is actually those categories for learning are defined in language. So they're language labels, even if we don't think about them as language-based. And so the new thing I'm going to talk about is in this right side, but introducing word-word relationships. If we actually do this kind of new step of like word-word relationships, we're going to get some benefits. And basically the biggest benefit that I'm going to talk about is my proposals are going to massively expand the types of visual knowledge that we can cover. So we're going to get lots of scale, but there's going to be lots of negatives in doing that. And I'll talk through some of them as we go. So I'm basically going to talk about two sets of works, one on understanding events in images called situation recognition, and a second work on kind of extracting graph structures from images based on caption work. And in each of these works, I'm going to give a benefit, which is almost always going to be scale, and then kind of a computational challenge that we need to solve in order to actually perform that problem. And if I have time, I'll actually talk about kind of my current favorite work, which is actually bias in recognition. So how, if we actually use language and vision to construct visual systems, will we actually impart our human biases into these systems, and that might actually be largely undesirable. OK, so just jump right in. So the first work I'm going to talk about is called situation recognition. This is work I've been doing for a couple years. And the basic thing that we want to do in this work is ask the question, how can we summarize what's happening in an image? And in this case, what I mean is in the image, there's going to be some sort of event taking place, and this event is going to be described by a verb. So in this case, what's happening is somebody's loading something. We're also going to be interested in the objects involved in that event. So in this case, there's a woman involved, a horse, and so forth. And kind of the crucial new piece that I'm going to introduce is an idea called roles. And roles are going to describe how these objects are interacting within the actual event. So it isn't that this is just a loading event that is randomly involving a woman. This is actually a loading event where the woman is doing the loading. So she's the agent of the loading event. And it's not just a random horse being involved. The horse is actually the thing being loaded, and so forth. So also the trailer, it's not a random trailer. The trailer is where the horse is ending up. After the loading, it's the destination of the loading. And to really see why this is important, you can construct these pairs of images. Basically, the key thing here is in both of these images, the core event is a pouring event, and the same objects are involved. So there's people, there's beer, there's glass. But I don't know, would anyone say that the same thing is happening in these two images? So we ask crowd workers, and the answer is almost dominantly no, right? And the distinction is really, well, in one case, the beer is ending up in the glass. In another case, the beer is leaving the glass and ending up in the person. So that's exactly the distinction that roles make. So So here's another example of how this might look. So here's a fixing situation, we're calling it. So fixing is happening. The one doing the fixing is a boy. The part that's being fixed is a tire, and so forth. And you might notice that that structure actually looks different than this structure. So the roles are different. So one central question is, where are we getting these things? Okay, what is the space of possible situations? And another question is, okay, if we actually define that space, how do we actually predict effectively into it? So now I'm going to talk about the first paper we had introducing this work. It was at CVPR a few years ago. The data set is called imSitu. And basically what we're going to do is we're going to use intuitions from natural language processing to structure that space. So if you're familiar with some problems in NLP, what I'm describing might have looked a lot like something called semantic role labeling. If you're not, I'm going to say it right now. So basically the problem is, given a sentence, so in this case, a boy is fixing a car tire with a tire iron outdoors. In semantic role labeling, you need to A, identify the verb, B, identify the arguments to the verb. So in this case, boy, car tire, tire iron, etc. And then lastly, you need to classify how these arguments are behaving within with respect to the verb. So it's not that it's any old argument, it's the boy is the agent, so the one doing the fixing. The car tire is the object of fixing and the part of fixing, and so forth. And so what we're going to do is actually borrow resources from these NLP problems to construct a visual recognition problem. So it turns out there's large ontologies supporting the recognition of these types of structures in NLP, and one particular one is called FrameNet. And it covers over 8,000 verbs in the English language. And so what we're going to do is we're going to just borrow the structure of that ontology, and that ontology specifies A, a verb, but B, verb-specific types, so verb-specific semantic roles to actually classify it into. So we're going to just take that ontology wholesale, and we're going to take a second natural language ontology called WordNet to actually be the noun categories that we fill into these frames. And so the problem setup is going to be, given an image, okay, A, predict the verb, and predict all of the objects and how they're participating within this structure. And so when we construct the data set for this, basically what we're going to do is we're going to just take images from the web and have mechanical crowdsourcing workers annotate these images with these structures. Because it's very kind of like close to how we would describe these things naturally in a sentence, it's very easy to do this at scale and communicate this information to crowd workers. So we've constructed actually a very large resource around this formalism. So it covers over 500 verb types, so each of those has unique structures with them. It covers over 125,000 images. There's nearly 2,000 roles specified, so those are those specific types of interactions. And despite actually having to pick from a huge quantity of nouns to fill in those roles, people agree quite a bit. So they were allowed to pick from one of 80,000 noun values, and 2/3 of the annotators agreed exactly on the same value over 75% of the time. So this actually is the largest resource currently for covering event semantics in images by over 100-fold in terms of the types of interactions and verbs and arguments that you can cover. So now we've specified this formalism. It's tied to a language resource. We've annotated at scale. How do we actually build effective models? And so I'm not going to go through this in too much detail right now. I'll actually come back to it, but I'll just give you the cartoon version right now. And basically the idea is to combine two types of machine learning. One is deep convolutional neural networks, and the other is structured prediction, so conditional random fields. And the basic setup is you're given an image, okay? And you take your current favorite convolutional neural network to build up a representation of that image. So back when I did this work, my favorite one was VGG. There's much better versions now. And basically what this module will do is it'll give you a vector describing the image. From there, what we're going to do is predict potential values in a conditional random field from that representation. And basically the conditional random field that we're going to use looks like the thing I'm showing on the left. What it's going to do is, so each of those boxes describes an interaction between variables in the structure. So for example, the box on the bottom right describes the interaction for verbs, whereas the box right above it describes the interaction relating verbs and nouns through a particular role. And the actual structure of this conditional random field we're going to use actually looks like a star. So how well does this work? Even this kind of like pretty naive setup, you can actually show some pretty interesting results. So one question you can ask is, okay, you've described this like whole structure, right? But is it actually important for predicting an event happening in an image? Okay, so let's say all I care about is predicting a verb. So is that verb happening in the image or not? Is it better to train a deep convolutional neural network to predict that label? Or is it better to use this conditional random field and actually use the structure for prediction? So it actually turns out it's better to use the structure rather than training a classifier directly on those labels. And you can ask the reverse question. So if I'm interested in objects happening in an image, is it better to just train a classifier to say yes, no, is the object in the image? Or is it better to pivot through this structure and use the graphical model to actually predict that an object is in the image? And turns out it's actually much better to predict objects through this structure than with a classifier on its own. And to get some intuition for that, imagine we're taking a picture of me this way, okay? And we're classifying whether I'm talking on the phone, okay? Basically, when this object is being used in this context, there's very few pixels supporting the classification of that object from your perspective because I'm including it with my hand as I talk on the phone, right? And so the only way to know that that object is there is to reason through the global structure of like, oh, this is a talking on the phone event, my pose looks in this particular way, and then actually know, well, it must be a phone. So usually I give a demo, but I'm trying to get through probably more material than I should. So if you're interested, basically all the data is online, and there's a really nice demo at imsitu.org. You could just like upload images, and it spits out these structures, and it's actually surprisingly robust. So I'm going to move on to the second part, which is, okay, so I've described one way in which we can merge, we can define a problem with respect to language and get huge scale from it. But this actually comes at a cost. And basically, I'm going to talk about that right now. And so the way you should think about this is, okay, well, what do we want our models to actually do? Okay, so currently we want them to predict these kinds of structures. This is a jumping event. But what kind of ways do we want our models to actually generalize? So currently in deep learning, if you hand a deep convolutional neural network 1,000 instances of a particular concept, and you ask it to classify whether that particular concept is present again in an image, it is very, very good at it. So what does that look like in our scenario? If we have different images of a person jumping from a cliff into water outside, and we've seen it 15 times at training, it's very easy to classify at test time another image with exactly the same output. Right? But can the model actually generalize to new combinations of things? So here's an example. On the left, so this is feeding structures. So someone is feeding something, some amount of food, some sort of food from something. So on the left, it's a man feeding a baby milk. The annotation of the food being milk, it happens 76% of time, or 76 times in our training set. The next image is a horse being fed. That particular piece happens 7 times, but the combination of the two never happens. Okay, so can we get our models to actually do that kind of prediction? So in this case, this example actually works, but what we really need to do to measure this is actually figure out a systematic way of telling cases where this is happening or not. So here's what we're going to do. We're going to develop a measure that we're calling semantic sparsity. And basically, we're going to take any test image and its annotation, and for every piece in that annotation, we're just going to count up how many times we've seen it in the training set. Okay, so on that agent being woman, that's happened 60 times. The eater being a horse, that happened 7, 76, 58, and 8. And we're going to assign a difficulty to this image, which is the minimum of all of those values. Okay, so this image gets assigned a value of 7. Okay? So what I'm plotting here is, on the x-axis is that difficulty notion. Okay, so the frequency of the most rare piece that we need to predict. Okay, and on the left, I'm plotting the accuracy of not even predicting those pieces, but actually just predicting the verb at all. Okay, and basically what you can see is, on the left here, as any one piece becomes rare, the model can't even predict on a high level what's happening in the image. Okay, so this is a pretty big problem. And it turns out, at least in the data that we've constructed, 25% of images live here. So what are we going to do? We're going to basically propose 2 kind of technical solutions to trying to fix this particular issue. One is encode better sharing between examples, and the other is to kind of leverage more connection to language. And so I said I was going to go back and explain this a little bit more. Basically, the thing that we want to try to change is this verb role noun potential in our conditional random field. And so what did it look like down in the guts? So what it looked like is we were going to take an image and we were going to produce a representation for that image. And then we were going to predict potentials in a conditional random field. And each of these potential values corresponds to the affinity of the image having any particular verb, role, noun combination present. Okay? And if you looked into the guts of the model, what there was for every verb, role, noun, there was a parameter vector. And that parameter vector was just going to test, just like a normal classifier, is that combination in the image. So it's just going to compare itself to the image through inner product. And we were going to do that for every possible verb, role, noun that exists in the system. Okay? But now I'm going to introduce a different way of doing this. And this way is going to encode more sharing. And so basically what we're going to say is, so instead of having a separate vector for every triple combination, we're going to introduce one vector for noun representations. So in this case, just brush. One vector for verb role representations. And then anytime we want to compute a particular value to see if that thing is actually in the image, we're going to take these representations and pass them through a shared function. And this shared function is going to try to predict what the image would look like in this combination. Okay? And then produce a vector and test whether the image actually has that particular property. The nice thing about this is the composition function is going to be shared across all possible verb, role, nouns in the system. So how this looks in practice is a bit more complicated because there's a lot of kind of black art to actually making this work. So I'm not really going to go into the detail other than there's like some tensor products testing these things. But you can definitely check out the paper. But so how does this work? Okay, so the black line is going to be this new model that I've introduced, and the red line is going to be the first version where there was a unique weight for every verb role noun. And basically, if you look into these rare bits that I identified before, nearly for all cases, this composition function improves the actual performance. So how much? This much. So about 1 point for actually predicting the verbs, and a lot more for actually predicting which nouns sit in those values. But basically, what I just described is very much the hard way of doing things. So just kind of like coming up with a model that'll like be able to predict which image, or like what the image will look like when you combine these things. It's just really hard. You're trying to grab this curve and pull it upward, right? But there's something really obvious going on here, which is if you could just move right on this curve, everything gets better. Okay? So is there a way we can move right? Okay? And there is. And basically we call it semantic augmentation. And it leverages the fact that these structures that we're predicting actually are very closely tied to how we talk about these things in language. And so if you have that frame, that structure down on the bottom, at least in English, it's very easy to realize that structure into a sentence. Okay, so in English, all of these arguments must occur in certain positions and in certain orders in the sentence associated with certain prepositions. So you can realize this thing as a woman loading horse into trailer with rope outdoors. And you can do this with templates. And so basically what we're going to do is say we're going to take every annotation that we see in our training set, and we're going to realize pieces of it into phrases. Okay, so if we had something like woman loading horse into trailer with rope outside, what we're going to do is we're going to generate a phrase which is a sub-piece of that sentence. So woman loading horse, or loading into trailer. And we're going to just take these phrases and retrieve images that people have described using those phrases, and use that as pre-training for our network. So how does this work? It turns out this actually helps irrespective of what kind of model you're doing. So basically, if you're interested in the base model, it helps about 1 point and helps 2 points for actually classifying the nouns. But it also helps the compositional model as well. And it turns out it actually helps the compositional model significantly more. And kind of the intuition behind that is when you retrieve images from the web, oftentimes they're accurate in terms of objects, but not accurate in terms of activities. And so you need explicit representations of objects to actually gain a lot from that data. Okay. So that's the end of this section. And basically, I'm just going to summarize. I've introduced a role-centric representation of what's happening in an image. It's based in language, and the roles describe the relationship between verbs and nouns. Its key upside is that it's large scale. It can cover a huge amount of the types of things that we'd like to see in images. But it comes with some downsides. So sparsity is a challenge. Things occur rarely supporting any one classification, but I actually gave a few methods for overcoming some of those challenges and showed actually quite large gains. I guess the images on the bottom I just like and can never really work into these slides, but these are actual images in the data set. And basically it's like a person or a man hugging a dog, a monkey hugging a cat. Can we actually do a prediction of a monkey hugging a dog? And you should kind of like see exactly why this might actually work. So, anyways, so I'm going to go on to the second part of this talk, which is about scene graphs. And this is a paper that we presented at CVPR just last year. And Again, it's going to have an upside of we're going to be able to kind of introduce a new type of analysis of an image because we're very tied to language, but it's going to have a challenge associated with it, which is global consistency. So what's the setup? This is a scene graph from a data set that was introduced from Stanford in 2016 called Visual Genome. In this image, basically, objects are described by where they are using bounding regions. And in the actual product, which is on the bottom, every object is a node. Every relationship between these bounding regions is an edge. And the task is to, given the image, produce this graph and those bounding regions in the image. And the cool thing about it is it's going to combine lots of different pieces of types of recognition, right? So we're going to need objects, so we're going to need to do object detection. We need relations, so this is like object-object interactions. And it's going to give us a global understanding of what's going on. So everything's going to be kind of covered with the relationships and their underlying types. So how does this actually come into existence? How did these graphs get made? And the way is actually very closely tied to language. So the way this data set was made is people randomly drew boxes on the image, and then they wrote a sentence about that box. So in this case, there's a woman riding on a motorcycle. And I've highlighted one particular edge in this sentence. If you're kind of familiar with some NLP, this will look like something called a dependency parse. Okay, and what it describes is actually the syntactic relation between those words in the sentence. So someone would have done that particular sentence. Someone else would have done a white motorcycle on the road. Someone else would have done a woman wearing a helmet. And basically what people did is they post-processed these captions and combined them. So edges that were repeated got merged together, and all the information in all the captions that people wrote down was covered. And so that's actually how you ended up with these graphs. And the thing that you should kind of think about is, well, every node-edge-node combination corresponded to some syntactic relation in a sentence that actually underlied this data set. Practically, again, the data set is quite large scale, so this 100K images. The actual semantics of what's annotated is 150 objects and 50 relations. But it comes with kind of like some caveats, which is you can't get people to describe everything in an image. It's kind of like an endless stream of things one could say. So practically, the graphs are highly incomplete. So what are the properties of this data? So we went about trying to study, like, so what? So we did this. It seems great. These are like very nice high-level descriptions. What's in there? And so we came up with this idea of trying to mine something we call memes. And so this is kind of like an old data mining trick that people used to do. It's basically relies on something called pointwise mutual information, which just tests how often things are co-occurring more than chance. And so what we're going to say is for every node-edge-node combination, we're going to call that an atomic symbol. Okay? And then we're just going to look over the data set and find atomic symbols that co-occur with each other more often than we would statistically expect. Okay, so that's what having a high pointwise mutual information means. So we're just going to threshold that. And then when we find those, we're going to replace those with an atomic symbol, okay? A new atomic symbol. And then we're going to run the whole thing again, okay? And so what is this going to output? It's going to output things that, big structures that co-occur together way more often than we would expect by chance. So here are the things we actually find in the data. If you have a flower in a vase, you can expect at least 8 flowers in the vase because it's likely not a lonely flower. If you have eyes of a cat, you should expect ears of cats. Or if you have things with elephants, you can expect the whole structure of elephants having trunks, noses, and all of these things. And it turns out these types of structures are really common. Okay, so for the data set, over 50% of images contain at least one of these types of structures. And these types of structures are actually a big challenge for models because they require outputting big pieces of information that must be together consistent. So what we've done is actually introduce a method for doing that. The key insight is basically to allow models to have access to arbitrary context about what they're outputting. And here's kind of like a sketch before I go into it of what this model is going to look like. So basically, we're going to do something, I'll tell you in a second, to construct object context. Okay? And then before we commit to anything, we're going to allow all of the object contexts to share information. Okay? And then we're going to commit and predict objects. Okay? And then we're going to share all the information we have about those objects to predict edge context. So like, what are the likely relations? And then we're going to commit to edges. Practically, there's a bit of a caveat, which is there's kind of like many ways you could imagine to pipeline this. But we have some statistical analysis that actually argues that this is the right way. And I'll just leave that to the paper because it's not too interesting. So how does this work in practice? So this is the model. It's called MotifNet. It relies on kind of like some basic computer vision machinery, so something called an RPN. And what does this RPN do? Basically, it just proposes regions that are likely to be objects. So that's the output on the bottom. So it's just saying, this is likely to be a dog, this is likely to be an eye, and so forth. And we're not committing yet. The second piece is going to be to establish context over these proposals. And this is just going to involve an RNN. So what we're going to do is we're going to lay down all of these proposed regions and run a LSTM forward and backward to share information about what information is in these regions. After we've shared the information, we're going to commit to the regions one by one and let a model know the previous committed values. So this is an LSTM generating left to right, the fact that the first region is a dog, the second region is a head, and so forth. After we've committed to those, we're going to share context between these committed values to establish context for making edge predictions. And in order to make the edge predictions, what we're going to do is we're going to enumerate all possible edges between these boxes. So there's going to be like a quadratic number of them, and we're going to compute some sort of outer product representation in order to actually say whether an edge is in or not. And to know what representation to use, let's say if we're trying to check if there's an edge between dog and eye, we're just going to look up the dog representation and the eye representation from this shared context and use those as feature representations. Okay, so I've proposed a model. I'm just going to quickly go into how you evaluate it because I think it's a little complicated for this setup. I think the hardest setup is basically putting down, so you start with an image, and so you need to put down boxes and that graph. So you can say, what is the accuracy, or what is the recall of getting a box and a label and an edge correct? So that's the hardest formulation. There's some weaker ones, so you can condition on knowing where the boxes are and just produce the graph. So that we're calling classification. And then there's an even weaker version where you can say, well, okay, I know all the objects and I know where all of them are. Can I just put down the edges in that graph? Okay, so we're going to call that relation extraction. And when we're testing whether or not we're putting a box in the right place, we'll just see if the boxes have sufficient overlap. What do the baselines look like? The baselines were proposed in 2017. Basically, they're similar to what we proposed in as much as they try to pass information between proposed predictions, but it's very different in as much as basically it doesn't allow as much global conditioning as we can do. And so here's how it works. So graph prop is that baseline that I kind of described. Basically, we've re-implemented it, a much better version. It works this way. Basically, so the most simple kind of structure that's important in these graphs is accurately predicting an edge given a pair of objects. And so kind of the simplest baseline you could imagine doing that is actually just counting up how often a particular edge type co-occurs with particular object types. So kind of having that in mind, like, oh, if you know there's an eye, you know there's a head, probably the relation is has. So that actually turns out to outperform this particular model. And the model that we proposed even further improves. And kind of the intuition you should have is, well, our model allows you to kind of globally share information, and getting those big pieces right is actually really important. And this baseline that I showed actually shows that those models can't even get the little pieces globally right. Here's an example of what it actually outputs. So the things in green are correct. Things in blue are false positives. So they're things that aren't annotated in the ground truth. And then things in orange are things you failed to produce at all that are annotated in the ground truth. So given this image of this person, I don't know what they're doing. They're holding a cell phone. This is the graph we produce. And the important thing to really notice here is there's a lot of green kind of corresponding around all the things you would expect a person to have. So man having hands, man having head, man having face. Okay, and so getting all of that prediction right all together is actually what this model is excelling at. Okay, so just to summarize this section, again, I've introduced a formalism I didn't introduce, but some people introduced it, that's called scene graphs, and basically it's a relational analysis of multiple objects in a scene. And kind of the key feature of it is that allowed us to do it is actually it's derived from captions. So it's derived from linguistic data and is related through the syntax. It's kind of very nice in as much as it can offer a very high-level summary of what's happening in an image and all the kind of visual facets of it. But it comes with this challenge that many of the annotations are kind of correlated, right? And when you make this output, you have to make sure that it's consistent. Otherwise, kind of the whole graph structure doesn't make sense. And we introduced a model that actually addresses that challenge and can do much, much better at this type of prediction. So I guess I do have time. I think I went a bit fast. But get to talk about the section I'm most excited about, which is bias and recognition. Basically, this is a paper some of us had a year ago at EMNLP. It won the best paper. It was called Men Also Like Shopping. And here's the intuition. So these are sample images from that first formalism I introduced for events. So it was from imSitu.org. And basically, because this formalism is tied to language and tied to us actually annotating images, when we actually annotate, for example, the cooking event, we pull images from the web. And when we did it, we actually found that 66% of cooking images are associated with women doing the cooking, and 33% are male associated with doing the cooking. And this shouldn't be really surprising if you guys have ever looked on images on the web. There's tons of kind of stereotyped bias there. But the big kind of surprise is actually if you train a model on this distribution and look at what its distribution on unseen data is, it's actually this. So a model trained on that uneven distribution won't just replicate the distribution, it'll actually amplify it. So if at the beginning it was a 2-to-1 preference for associating women with cooking, now there's a model that has a 4-to-1 preference for associating women with cooking. And to really kind of understand why this is likely happening, that the explanation, I think, is actually pretty easy. It's actually good for accuracy. So if the model is uncertain about any one prediction, it makes sense to bet with a bias. Right? So in this case, the model might not know whether this is a man or a woman doing the cooking. In general, it's been women in the data, so let's just guess woman. But this is actually a problem, right? Because so the model is going to make a mistake, okay? Because the test distribution and train distribution are similar, so it's making a mistake, right? But the question is, what kind of mistake is it making? So imagine you have like a robot or something that's, for example, trying to help people in the kitchen, right? And then this boy goes up to the kitchen, and the robot doesn't know what the boy is doing. Okay? But it says, "Why? Let me help you fix the faucet." Okay, fine. But then the girl shows up and says, and the robot says, "Why? Let me help you get the cooking done." Okay, in both cases it's wrong, right? But how it's wrong actually matters, right? Because in these cases, the model is actually reinforcing gender stereotypes for these images, and this is pretty undesirable behavior. So I'm going to talk about our work in the space, and basically we're going to rely on that data set that I introduced at the beginning of the talk for events. And just to remind you, the way this works is there's an image, you pass it through a convolutional neural network, and the output of that convolutional neural network is used to construct potential values in a conditional random field. The structure of this conditional random field is important. Basically what it does is it allows you to tie predictions between the global structure and any one particular object, right? So I gave you that example with the phone, right? Here's another example with the spatula. In general, it's completely obscured for the cooking, and the only way to know that it's there is to understand the global context, right? So that this is a cooking event, and in general, these cooking events will involve a spatula. And that introduces a dependency between cooking and the value spatula. But we don't know which dependencies are important and not important, so we introduce it everywhere, right? And so that means there's a dependency between cooking and woman that we need in order to be accurate. But that dependency can potentially be problematic if we're not careful about it. Yes, and this is me repeating that we need these variables, but that's exactly the machinery that can be co-opted to actually produce a result like what I showed. So how do we measure whether this is happening? So measuring this is really easy. First I'm going to talk about measuring it on the data set level. So is there bias on the data? And basically all we're going to do is count. So we're going to count the co-occurrence of any particular variable with man or any particular variable with woman. And then just compute the ratio. So how does this look? So across the bottom is that ratio. And every point here is a particular concept, so a verb in the data set. And basically, here are some examples. So on the left are things that were more associated with women than men. On the right, there's things that more associated with men than women. And I think in principle, these things will make sense, but there's very kind of strong gender biases here. So in general, the things on the right are kind of like positions of power. The things on the left are things associated with home things. Yeah.
So you just randomly shuffle those the verbs, or is it? So it's not like monotonic, right? So I was wondering how do you order them?
So every verb is associated with one ratio, which I said here, right?
Okay.
So that's the dots along the bottom. And the graph is just saying, where are most of the dots? It's just computing the density. Yeah, exactly. So basically, most of the items are to the right. Yeah. Like I said, most of the items are to the right. So that means, in general, the data set has more men than women. So 65% of the entities are associated. 65% of the entities at all in the data set are male rather than female. And on the edges, actually, nearly 50% of events actually have strong bias. So 50% of the events are associated with one of the genders by a ratio of more than 2 to 1. So the gender bias goes both ways. So some things are strongly associated with men and some things are strongly associated with women. So the second part of this is actually measuring what's happening with the model. And the way we're going to do this is really just take unseen data and evaluate the model on that unseen data. So given unseen images, produce predictions. And then from those predictions, we're just going to count the same thing that we counted before. So the association of man or woman with any particular event that the model is predicting. So here's that, and I'll explain this. So across the bottom is the previous graph that I showed. So this is on that training data, what was this ratio for any particular concept? So for any particular verb. On the left is for unseen images, what is this ratio? And so if the model were perfectly predicting the same ratio for training from the training distribution on the testing distribution, all the points would lie along this blue line. Okay? And so the thing that we're worried about is actually here. So anytime a model had some sort of ratio and made it worse than originally. So that's highlighted in these amplification zones. So what are some examples? I guess I gave you one in the intro, but cooking was significantly more associated with women after training. Something like washing is now exclusively associated with women, so the model just never predicts that men are washing, irrespective of what's in the image. There's also kind of like male stereotypes, so men are now always putting things together, whereas women just aren't. And so it turns out that 70% of concepts actually had this bias amplification effect. And the magnitude of the effect was around 5% across the whole data. Practically, if you had higher initial bias, you actually saw more amplification after you trained on it. So if you were on the ends of these graphs, you saw nearly 50% more amplification than if you were in general. So here's the goal. So we'd like to build a model that's at least as good as the original and not more biased than the actual underlying training data. So this is kind of like a very weak fairness goal. And so I'm going to give you a quick sketch of how that works. Basically, we introduced this method called RBA, reducing bias amplification. And essentially what it's going to do is it's going to be a corpus level ILP over the predictions. So we're not going to require retraining of these models. And we're going to use Lagrangian relaxation. And I'll just kind of sketch it, but kind of the key idea there was if you have a structured predictor, Lagrangian relaxation gives you an efficient way to try to solve this ILP. What does this ILP look like? So the first part of the ILP is a score. So it's maximize some score given an image for some prediction y. So this is kind of like the most general version that you could imagine. In practice, that score is decoding from the conditional random field we had in this model. There are constraints in this ILP. And basically the constraints say for all concepts that you're predicting, so in this case events, the training ratio across the whole data set and the predicted ratio shouldn't differ by more than some margin. And so to kind of have this in mind, so on the bottom I've drawn a cartoon version of this. It's the same graph that I showed, training versus prediction. Every point is an event. And basically what we want to do is we want to take those red points which are exceeding a margin and bring them within the margin. That's the constraint we're trying to do. And so this is the hope that after we solve that ILP, those points will move in. And so how does this actually work? This is a very, very high-level sketch. Basically, you can solve this program using something called Lagrangian relaxation. And what it does is it allows you to iterate between doing the inference in the structured prediction problem that you know how to do, and then integrating the constraints into that inference problem. and adjust weights of the actual predictions. The high-level intuition, I guess since I'm not going to go through the example, the high-level intuition here is actually you want to adjust weights that you're not confident on. So if you think you're going to make a mistake, those are good candidates for changing the prediction to not be gender biased. And so that's what this program is going to do. It's going to try to find some small adjustments to places where the model is uncertain so that we can rebalance the ratio. So how does this work in terms of performance? This is exactly the plot I was showing you before, only now I've drawn in this margin constraint. And every red point is a violating point, and every green point is currently in the margin. And so after we actually run this debiasing protocol, we've reduced the number of violations by 25%, the average magnitude of a violation by 50%, and actually you don't really suffer a penalty in terms of accuracy for doing this. Okay, so just to summarize, so I guess I started this talk saying, well, we want to build a visual or a system which can recognize tons of information about the visual world. I propose that this is going to have to function through language, and basically I introduced this kind of implicit structure, where if we do this implicit structure, the kind of big benefit is we get lots of new types of information about what's in the world, and we can scale to a big diversity of types of concepts. And this came with technical challenges, which I tried to address. And the biggest of which is the fact that if you tie these predictions to language, you inherit a lot of the biases that we have in communication. So I'm going to give you one slide on future work. I showed you this picture to begin with, and kind of maybe it was like a robot reading a book, learning about the world, right? But I didn't actually give you a talk about that. I gave you a talk about downloading internet photos and then annotating them with some language-inspired annotations. And this wasn't a robot at all. It was actually just like a disembodied computer. And so I think a big kind of way forward is, can we actually really integrate language in a more natural way for recognition? And the thing that I have in mind is, well, can we think of something like humans giving advice to actual robotic agents? So instead of explicitly annotating all these things we know about language into the structure of some data set, can we just have a person naturally refer to objects, events, and relations as necessary for a robot to complete some sort of task, and the robot kind of implicitly learns all of these structures that we've been trying to annotate. That's really it. And these are all the people that helped contribute to these projects, and I'll take questions.
Really quick question. So I think in the graph you showed, the what do you call it, the bias graph, I think that was really big. That one on the right. That's very big outliers. Just wondering what that was. Do you know what that is?
I don't know what that particular point is. Yeah, but in general, right, so each of these points is a whole concept. So it corresponds to 50 images. So, I mean, I think there's some noise in the estimate, but yeah, I don't know.
When you try to debias the model, you said that when the model is uncertain enough, the model is to select less gender biased word, and doesn't that decrease the accuracy?
So practically, we know it doesn't really decrease the accuracy, and part of the reason is if the space is so large, the set of possible predictions, if you know the model is unconfident, that guess isn't actually that useful. So the amount that it's helping when the model is very uncertain is actually very, very little, and those are exactly the cases we're changing.
So after the uncertainty, is there any tendency of the safe, safe words for that? Certain words. The model thinks that this word is not generally biased.
So is your question, are there still biased predictions that it's making after this process is done?
I mean, so if the model is uncertain, the model is to change their action, change their prediction to another words. And is there any, sort of mode collapse for that kind of words? So safe actions.
I see. So you're thinking maybe actions.
Maybe if the model is uncertain enough, all the
Like
uncertain
all
predictions
these,
are
all
collapsed.
these things get pushed to the center.
Yeah.
Yeah, that's what you're thinking.
Is there any?
Yeah. I think practically no, because I think that would have a big effect on the accuracy. Yeah. I mean, I think the thing with this work is the amount of changes it's actually making is not huge, but it's affecting the statistics a lot. So yeah, for the cases that are safe enough, or where the model is slightly confident, it's definitely not changing it.
Also for the image situation, the situation task, the imSitu data set, I wondered in reality, the data set actually kind of make a structure of the sentence, right, describing the situation in a very kind of not in a very deep way, right? For example, it can say a woman is cooking, but in reality, it can be a woman with a red hair is cooking. So yeah, the kind of the description can be more very detailed or complex. So, but in fact, it doesn't seem like it covers that all cases. So I think that is a limitation of such an approach. So what is your opinion about?
Yeah, I completely agree. So I think, at least for situations, the target was objects and events or verbs, so nouns and verbs. So it absolutely doesn't cover attributes or yeah. So I think that's part of my thinking for we really want to be doing sentences, right? Because the sentences end up covering all of those phenomena, right? The reason that you could say it to me, right, is because it happened, because you said it with a sentence, right? But I think that comes with other challenges. And the biggest one is bias in terms of sampling those sentences. So you might extremely rarely see that redhead, or never at all that particular description, because it's hard to make people generate diverse language. They'll kind of just generate the same language over and over again. So I think that's one way in which the explicit structure is actually better. Because if you have that structure in mind, you can force people to describe things in different spaces of that structure. So if you're never going to use the word baking for some reason, and I know in my ontology I have the word baking, I can force you to annotate information about the word baking. But yeah, I completely agree. That's one limitation, yeah.
So do you think, considering the limitation, but actually, explicitly using the structure actually helps, you just mentioned, it really helps for, situation recognizing tasks, some of that. So considering the limitations of both approaches, using sentences or using the explicit kind of annotation, what do you think is the way to go, and what is the thing that you actually want to end up with?
Yeah. Yeah, I mean, I think, to be honest, I don't know where. I mean, I think there's some room for both. So at least for the explicit structure part, we're learning something about building the models. And at least we have enough diversity to really have confidence that our model structures are right. But honestly, I think the thing I said at the end is like really the way to go, right? Because like if we kind of know what the structure of the model should be because we annotated enough kind of like baby cases of this, so like situation recognition, then we'll know what to put in to make the system understand like the human utterances and all the diversity. So I think they maybe have different roles, but I think ultimately it should be sentences.
Is there any approach that has a different objective of that gender bias and that actually makes the target line to like not y equals x, but like y equals like 0.5?
Yeah.
Yeah. So like maybe explicitly decorrelating gender word and the data.
Yeah. So yes. So basically, the group that I've been working with on that bias stuff has been looking at different versions of the problem, right? And so one thing that you could do, right, is like, okay, you have this data set, right? And you know it's biased, but you could just subsample the data such that it's equal, right? And then make that like the learning objective. Like, do things still go wrong? And it turns out that the model still learns gender-biased representations that amplify. And the reason for that actually is because just because you've balanced the data doesn't mean there's something in the image that isn't still correlating that you didn't balance for, right? Because the image is filled with many unannotated things, right? And you can't actually balance all of that, right? Because you don't know what they are, they're not annotated. Right, and so even if you balance, actually, you get this bias amplification effect. So it's actually really hard. But yeah, so there might be a paper at some point soon coming out that looks at like how to do better at that with kind of like some adversarial learning techniques. So chat about it offline if you're interested. Okay.